So it's certainly a pleasure to be here. I was away from the field for a few years, helping the Brazilian government to put together a national laboratory in ethanol. But during that time, I pointed some of my electromolecular scattering efforts to a Brazilian agenda of making more ethanol with sugarcane. It's I just give you a very short motivation for this problem. But what we have in Brazil is an economy running with cars, a flex fuel car. So you have ethanol and gasoline in any quantity, in any gas station in Brazil, and you can choose if you use ethanol or gasoline or any mixture of them. And one of the, of course, the flex engine cars, you have to understand ignition, you have to understand what the best mixture, how to make the best car, start plug, and things like this. So this was a beginning of a motivation of looking into problems, and including to take a look on alcohol molecules, electromolecular scattering, of all different kinds of alcohol, including those that can be a drop-in field because they are large enough, they have energy that you can just put in the car and you don't have to adapt the car itself. And from a larger motivation was we do have a large-scale production of ethanol. We use the sugar cane, and it's a kind of biorefinery because you produce electricity, you produce ethanol, you produce sugar, and in different mixtures. And a question that we asked there was the biomass could be a great source for energy and products, carbon. And instead of burning it, you can do something better than this. And the first generation ethanol was done by crushing the cane, using the juice, and then producing ethanol. A second generation would be get these big mountains of biomass and separate the cellulose. Cellulose are polymers with a lot of sugars, and learn how to break them down. More sugars, more ethanol per hectare, that's a good business. And on top of this, the question is, can you do other byproducts with higher values? So within this circumstance, I motivate some guys from chemical plasma physics to see how can we use a discharge environment to help to separate the cellulosic material from lignin. And if you take a look in any plant, you have a structure made by the lignin, and you have the cellulose and the hemicellulose. So if you want to do biochemical strategy of separating the cellulose, you have to do first to take the lignin out. So the question was, can you use some atmospheric plasma to make a discharge environment and see if you can help to separate the lignin from the other products. And so that's the beginning of that motivation. So there are some groups, and I'm going to spend some time on this, using this strategy and see, okay, if you do a discharge in such a biomass, who is going to break? What kind of molecules are going to see? What kind of... And what we learn is that the lignin, just being quite quick, but the lignin was removed more quickly than the others if you do the discharge environment, and the question was, why? What's going on? And following the steps of using low energy electrons to study resonance and breaking down DNA molecules and so far, we went to take a look, remembering that we have a quantum mechanical problem, that we are passing through different pieces of the molecule. And what we did was attack each of the components of the biomass using the Schwinger multi-channel method. So to go back to the topic of the conference, let me just give highlights on the method and pointing the uncertainties. Where are the uncertainties in the Schwinger multi-channel method? And then I will make some applications where Some of them you don't care too much about uncertainties because you're learning something new, physics. Some of them you have to be very careful and understand what's going on, otherwise you produce bad cross-sections. So remember that we are solving the Schrödinger equation and the Schwinger-Muth-Channel method. You start in the Lippmann-Schwinger equation and we end up using a green function. As a matter of fact, instead of having the full continuum of the target states projecting the green functions, we use only part of it. And, but by using the green function, that's the first source of uncertainty, because in the beginning we didn't know how to do that, and then we start doing plane wave expansions, we learn, we control that. You can maybe not call an uncertainty, but an error that we have, you know, how to control. Another thing is the variational method. I don't know if you remember how that's developed, but it allows, because we always have the wave function multiplied by a short range if you don't have a dipole moment potential, if you don't have ionization. That allows you to expand the wave function in an L2 expansion. That certainly is a source of uncertainty, but again, controllable if you have sufficient computer power. And the way the Schwinger-Muth-Channel method was put in together, that's the final operator A plus of the last slide. And then we do have a projected open channel space. And that channel coupling, here certainly is a big source of uncertainty, because what people are saying here, that you have to define which states, that's the main approximation. You are throwing an electron that may be with 15 volts, and you have sometimes a continuum of states of the target, and you have to make choice. You throw some of them out. And I say it's uncontrollable because I'm going to show some results that is pointing to that direction. Another thing is, you also have to define your n plus 1. You remember, I have all the problems of the fixed nuclei approximation. I have a geometry, we're scattering a molecule in a particular geometry, and the scattering wave function is a combination of configurations, you know all the terms. And this is again, certainly, where you interrupt that, how many functions you put, the combination of this L2 bases in the last slide with the number of targets that we have for open and closed channels. That certainly is not something that converges quickly, that you say, oh, I know exactly the answer. Is certainly a source for uncertainty. Controllable in the sense that if I fix the number of states and say, I'm going to solve the problem for 10 states like this, and somehow we can converge that situation. If you're going to get the right response, that's another story. And so just to place the approximations I'm going to show in the right perspective, if you talk about elastic scattering, we can do it with and without polarizations. In the elastic scattering, the ground state only participates in the P operator. And our target description has a problem, a source of uncertainty, which is at present implementation. We don't have a Hartree-Fock approximation for the ground state. And again, if you have only these states, you're going to work with the static exchange approximation. That means scattering waves associated to the ground state itself, or excitations of the target. We use single excitations of the target associated with the n plus 1, given the n plus 1 wave function. And of course, if you have a closed shell molecules, you have only doublet states if you on your expansion. Okay, if the next step, if you want to do inelastic scattering, then you have P more sophisticated with possibilities of exciting. We can excite singlets and triplet states. And again, your choice and the limitations of the description of the target can give rise to problems. And the excitation space, configuration space is similar to the one before. of course, now this space will have not only the polarization part, but also the channel coupling part. Okay, and on top of that, we also, because we want to look some molecules which have big number of electrons and sometimes with relativistic effects, we introduce pseudo-potential formalism, but that's certainly is a source of uncertainty, but is optional if you are dealing with light molecules because you just don't use them. But normally we get reasonable results and controllable results with the pseudo-potential strategy. Okay, so what I will do first is take a very short visit on problems that we learned that a lot, even if you don't have, we are not absolutely sure that we are doing the most precise calculation. And one of them is based on what you have seen a lot, shape resonance on these molecules. And I'm not going to go through this, but everybody knows the mechanism of having a resonance, having a sigma resonance, and how those things will may break the molecule down through some particular virtual state that's going to expel a hydrogen or some molecule. So what we want to do is take a look on the lignin structures, and if you look in the lignin, you find all these kind of molecules in the lignin. So, of course, as usual, what we do is we got a little piece of it and see how much we can learn from that. And we really found interesting that all these molecules will have lots of those shape resonance, indicating that it's an important path for breaking down the lignin and supporting the observations. The mechanism we have seen is similar to what you have seen if you look at where the resonance states, how we are going to have the virtual state, the hydrogen being popped out from this. So all the mechanisms that usually we see in this kind of thing, we've seen in this family of molecules. At the same time, we took a look in small pieces of the cellulose and the hemicellulose parts, and we saw no resonance of the same type. And but of course they are susceptible to dissociation as well, but not with the same mechanism and with the same strength. And a second motivation of something that we can take a look, and not having a very precise calculation, is something in this, when you start looking into problems with a very specific application, especially if you're in a biological environment, you have to ask yourself, what's the role of water? I mean, if you're scattering a molecule, and how the water will affect your cross sections. So we did some calculations with formaldehyde, where we learned first that if you have this is a system where, before let me explain, what we do is a Monte Carlo calculation. We have a group doing this kind of work with us, and they find the best structures, the most common structures of water reaching the molecule. And then we are going to say, still in the gas phase, let's scatter that system and see what you can obtain. And what we learned is that in this first paper we did, we have the water molecule. It was a coincidence, but it was always donating a proton to the formaldehyde, somehow pointing is a hydrogen bound, and the hydrogen is being given to the scatter center. And what we found at that moment is that the resonance that in the free molecule were around 1 eV, they lowered down. So somehow the water molecule was lowering the resonance down. And that's a qualitative study, but it will tell us. So maybe at that time we believed the solvation was helping the dissociation somehow, if it's going to be through this kind of mechanism. On a second study, again, now we had the water molecule donating protons, like these ones, and some of them receiving protons. It's like this one. And then what we learned by studying the resonance is that when the proton was being donated by the scattering center, we had the same phenomenon. You have a positive charge coming in, you have the resonance moving to lower energy. And on the other way around, it's like you unstabilize the resonance and goes to the other direction. And just to finish this motivation part, we did the same thing with phenol, which is now a piece of the lignin, and we saw the same thing. In particular, in the phenol case, we had a situation where we had two molecules of water molecules, one donating proton, the other one receiving proton, and the competition among the two processes, and it was, again, quite interesting. And I'm not going to discuss this detail, but I want to show another thing that we can learn is with the solvation, what kind of difference would you expect in your differential cross-section? I mean, with the limitation of the method, what can you get? Remember that, suppose you have a gas, water molecules, and phenol, and somehow they are solvated in a particular way. If you shake that and somehow break all the water molecule bonds, you have a mixture of gases. So you expect to see an average differential cross-section like this. Now, the difference between the blue and the green curves are the electron is scattering these many molecules, but a group of them is really solvating the phenol molecule. Somehow, so they are rotating together. You have all the collective, the group of phenomena together. And that's the kind of differential cross-section. And sometimes you may have bigger than error bars, sometimes not so big, and learn how to understand the solvation of this system. So now I'm going to talk about the limitation with particular focus on the electronic excitation. We discussed many of these issues in this conference. And for many years, we believed, at least, that if you make a smart choice on electronic states, and you choose the right ones and put in your calculation, that you're going to get very good results. As a matter of fact, we just discussed here that we expect, for instance, the distorted wave calculation at high energy to give reasonable results if you go high enough. So the question is, how correct is this in terms of a number of open channels that you are introducing the calculation? So just to start with, in the past we have done this. This is a two-state calculation with the Schwinger method on H2. This is with few state calculation. Only the lower H2 states are participating. And at that moment we got very excited about good results. There are matrices here also on this. And we understand that the channel coupling with few states were giving us a good solution. For some systems like N2, we quickly learned that the Hartree-Fock approximation in the target was not a good approximation, that we have to improve the target. So that's certainly a limitation. But for some states on N2, we also have very reasonable results. And maybe the last one before I left was ethylene. And that's how I start to discuss our limit uncertainties. At that moment, we are studying acetylene, particularly the lowest B triplet state of acetylene. And I don't know if you recall that, but the acetylene has a resonance, a shape resonance. If you treat this, if you treat this in the static exchange approximation, the resonance will be on the right side of the first threshold. If you polarize, the resonance moves below the threshold. So the whole dynamics of the electronic excitation will change completely because of that. And we learned that. So those are the at that moment, those are the close coupling calculations, like no polarization. And when we polarize, we found reasonable agreement with experiment. So that means even if you ask myself, have you control your two-state calculation in a sense of expansion of the scattering wave, the target representation? Yes, we had some control on that. But there's something else happening, that particular resonance, polarization, would move the resonance and could change a lot the cross sections. So when I was invited to this conference, I said, okay, let's continue this and see what we are seeing at higher energy, something that's maybe working at low energy. Let's see if I go up in energy. Michael Brunger has had new results on ethylene. Let's say I'll continue and see if something that I thought we had understood continue in the high energy spectrum. Oops. And at 30 volts, you may believe maybe this experimental data is wrong. This is about 20% error bias. I didn't put it here. The same approximation I use on those two energies at low energy, just right the threshold above the threshold, give very different results of almost order of magnitude. So the question we asked is, what's going on? So within the limitations of our computer codes, we said, okay, let's get the same base set we used before and run a full single CI configuration interaction for the excited states. And after that, in order to not put all the configurations in the program, that would be too expensive, we had a minimal orbital-based single configuration interaction. And in the sense that we would put all the states that we have in the full single CI approximation would be there in our poor approximation below 10 eV. And by doing this, the first thing we learn is, even if you take a look in your elastic cross-section, you'll see that the elastic cross-section using the one-channel approximation, and the two-channel got a little better, and this is the 17-channel approximation. For that energy, we have the 17. So the excited states were changing substantially, especially at this angular region, the elastic cross-section. That's something we learned with this optical potential complex potentials. But now this is it's fully ab initio in the sense that we are putting all those states together. And if you continue on the 15 volts, again, you see those, if you put this in a non-log scale, you're going to believe everything is well. But as a matter of fact, we have, this is almost 1, this is 0.5. There's a factor 2 difference in the differential cross-section. That is due to multi-channel coupling. Even if you continue on the 20 volts, you see this is a 45. Here I have 45 closed coupling. I have 45 open channels in this in the ethylene, and but I was quite happy with my elastic cross sections with this, because it's really going towards the right answer as I increase the channel coupling. And if you look in in the last 30 years, probably everybody doing elastic cross section, they don't couple with the inelastic one. They just do, let's do, if you are sufficient low energy, use only static exchange plus polarization, and you really don't go further on that. But certainly, this is extremely important, as you can see here. Not everybody, but some of them will do this. And what was kind of, and that continued to 30 and so on. But the question is, are we convergent? I mean, what is the uncertainty of your calculation? You decided to put all the states you had on single CI excitation up to 10 volts. Can you be sure that you have the right answer? And by looking at the different elastic cross sections, I would say I'm quite happy with this. By looking at the low energy excitation, using now at the same calculation I did before, now with this new strategy, we had very reasonable results. But when I start increasing up the energy, unless this is wrong, I'm not seeing going to the experimental data. Even if sometimes you're very optimistic and see I have 3 of the 4 points, but this one I don't have it. So it's what's going on. And if you continue going up in energy, what you start seeing is the cross-section, that's a 2-state. That's a 17-state calculation. Oops. It's trying to communicate with This is the 45 channel coupling. At 20 volts, you see, at 30 volts, this is almost an order of magnitude lower in energy. And that's something, if I have seen this 30 years ago, I would say, of course, I understand that. Because if you have a river flowing and you have a lot of gates there, if you start to open new gates, the flux on each of the gates will decrease. So that's what you're seeing. You're opening more gates and the cross sections are lowering down. And going to the right direction. But certainly that's telling me that I have uncertainties going on. I don't know how many more channels do I need to go even further and when that's going to stabilize.
Sorry, isn't the answer to that infinite? Because you're in the electron continuum.
Yes, but I mean, maybe you're going to share those cross sections and somehow integrate the density of states, and that's going to give you a finite number. It's not going to give infinite cross sections.
But then you use convergent close coupling or similar RMPS type methods that you have to get representation of an infinite number of channels.
Yeah, so?
Well, you asked the question, I get
Okay. But anyway, so that's at 50 volts. And certainly, if you run perturbative methods here, you're not going to find, you might even find cross-section at low energy, but I don't know if you have the right physics on that. And so that's the first thing I'd like to point. And just to confirm that on the inelastic case, we went back to phenol and say, listen, this is something we published 2 years ago on phenol, and that's the elastic cross-section using a more correlated target system, more correlated n+1 wave function, polarized space. This is something, now we want to run a calculation with a big number of open channels on phenol, and because of computational limitation, we decided to run the same base set we had before, but a smaller configuration space for polarization, but up to 33 open channels. So it's a 33 open channels competing to each other on this calculation. And when we finish, we are doing this in collaboration with Michael Brunger and Maria Cristina Androli Lopes from Brazil. And they are not going to do the last case anymore. So we look for something similar to phenol, and by looking at the benzene molecule, our differential cross-section in the Lask, in the most sophisticated case, here 15 volts, so we have only 23. When I go up in energy, I open up to 33 channels, and the cross-sections looks more very good indeed. And that's not something we calculated with the benzene cross-sections with us, with just 5 minutes. So that's something we did, and then we put the data here. And it's impressive in good agreement with this benzene molecule. At 40 volts, that may indicate that we need more to open more channels in the situation, if that's the only reason for. And if you take a look in the momentum transfer cross-section, you see if the momentum transfer cross-sections using only one channel plus polarization, they were here in the two calculations. Now with the multi-channel coupling, you're looking at the last cross-section and calculating the momentum transfer cross-section. We got very in the error bar of the experiments. Of course, that's the reason we had the differential cross-section working well, and that's what's going on. And just to finish, very fresh results, I got this last week from Michael. Sorry, there's some. They have resolved the electronic structure of phenol, and they cannot separate the first triplet from the second triplet, so they are summing the two together. And this is what they are finding. Very unusual cross-section for triplet states, very flat. But the point is, when we sum our first two states, it's also very flat, and about 12 times bigger than what you have here. So, if that's the meaning of this is you need more channels, but that's what's going on. So the message is what we focus in electronic excitation process. I think we still have some dogmas that we believe if you go to high energy, some particular methods should work, but what I've seen today, even in your calculations, Jimena, on water molecule, maybe what's missing is the other states to lower the cross sections. Maybe, so I think we should really pay attention on the possibilities of not believing that this two or little close couple, I mean, we learned this from the atom case, but in the molecular case, it's going to be a nightmare if you need to put lots and lots of states, but I think we will have to do it in order to get reasonable results. Now, beforehand, I think if you say, can you control this? When you start a calculation, say, do you know how many states you should include? The answer is no, I don't know. Do you know how big is the configuration space? I'd like to point, I don't know, in the Schwinger method, when you write the many-body wave function and you find a variational stable solution, and when you can write down the wave function as a combination of those configurations, that same wave function goes to every transition, including transition among excited states. It's the same solution. So you do a variational stable method, but you're not only solving the last case, you're solving all the process at the same time. And by doing so, it's extremely difficult to control your approximation. If you have a Rydberg state, very big state, very long range potential, do we have the Cartesian Gaussian functions to describe that? Probably not. So it's a big challenge. And I stop here. Thank you very much.